This screen demo introduces an educational function of VisualFEA, related to eigenmode simulation. The function is useful in teaching and learning the concept of eigenmodes and their implication in finite element behavior. This demo suggests how to use the eigenvalues and eigenvectors of the stiffness matrix for examining the characteristics of finite elements. There are various aspects of finite element analysis that can be studied using the eigenmode functions of the program. A part of them will be shown here as follows. Physical analogy of eigenvalues and eigenvectors to mechanical behavior. Graphical representation of eigenmodes, based on the physical analogy. Components of displacement modes. Rigid body modes in a single element and assembled configuration. Effect of boundary conditions constraining rigid body modes. Effect of numerical integration schemes on eigenmodes. Spurious zero-energy modes and its characteristics. Communicable and non-communicable mechanism. Linear combination coefficients and modal coordinates. Force contribution factors. To start the program, select New Item from the File menu. Then, Project Setup dialog pops up for the setup of a new project. Click Plane Stress or Plane Strain Radio button, either of which does not make any difference in the contents of this demo. Click OK button to complete the project setup. In this demo, a quarter part of a plate with a hole at the center is set as the study model. Create a circular arc and 4 straight lines, consecutively. A closed region boundary is formed for a planar mesh generation. The grid may be turned off, as it is not needed any longer. The density of the mesh is determined by the division of the boundary curves. Select the circular arc and divide it into 4 segments. Select the 2 lines bounding the top and right sides, and divide them into 4, respectively. The mesh will be generated to fit the divided curve segments. Accordingly, small elements will be generated, facing the circular arc, and large elements in the upper part. And the size of the elements is gradually varied in the middle. Choose Auto Meshed Surface item from Mesh menu. Auto Meshed dialog opens, and Region Selection button is pressed automatically. In the dialog, set the element type as quad only. Click Automatic Curve Division checkbox, so that the undivided curves are divided automatically, for optimum mesh generation. Place the cursor over the region bounded by the curves. Then, the region is highlighted in green color. Double-click the region. A mesh of quadrilateral elements is generated in the region. In order to assign element properties to the elements, choose Element Property item in Assign menu. The property item of plane strain case includes the modulus of elasticity and Poisson's ratio, as factors, affecting the stiffness matrix. Let's use the default setting. Bring the screen cursor over the mesh, and double-click it. The property set is assigned to the model. Now, we can start examining eigenmodes of the model. Choose Eigenmodes item, from FEM Simulation submenu, of Solve menu. Eigenmodes window appears on the right top. Plane Element Selection button is automatically pressed. Drag the model image to a proper position. And, select an element by clicking it. Then, the eigenmodes of the selected element are displayed in the window. The eigenmodes are initially represented by the deformed shapes of the element. The graphical representation is based on the physical analogy of the eigenvectors to the displacement modes. The eigenmodes are drawn, in the order of corresponding eigenvalues, from smallest to largest. They are aligned in a specified number of columns, which can be set, using the drop-down list menu. The gaps between eigenmode images can be adjusted using the alignment function. The first 3 modes are paired with 0 eigenvalues, and thus, called zero-energy modes. If you click an eigenmode image, the deformed shape is animated. It is rigid body translation in x direction, in y directions, and rotation. 3 zero-energy modes are identified as rigid body modes. Other modes are deformation modes representing bending, shear and axial deformation. Click Stop button to end the animation. Click +- button to reverse the sign of the eigenvectors. The eigenmode can be represented by image of strain contour. Click Contour Radio button. The strains are evaluated based on the displacements derived from the eigenmodes. A strain item for contour image is selectable from the drop-down list menu, such as normal strain X, or normal strain Y. The strain state can be evaluated more synthetically using the strain energy density. As indicated in the image, no strains appear in rigid body modes. The uniform color of the last mode implies a constant strain state. The integration points for stiffness computation can be marked on the eigenmode image. 4 points for 2x2 integration are shown. The integration point will be explained later with regard to zero-energy modes. There are other options of representing eigenmodes, such as vector image, or numerical text. Let's go back to the wireframe representation of deformed shape, and examine eigenmodes of assembled configuration. Select multiple elements. Now, eigenmodes are displayed for the assembly of 4 elements. The window contains only a part of the images. Reduce the image size using the slider control, and adjust the gaps between images using the alignment tool. The images can be scrolled up or down by mouse dragging. There are 18 eigenmodes, because there are 18 degrees of freedom within the assembly of 4 elements. Click an image to activate animation. It should be noted that there are still 3 rigid body modes for this assembly of elements. Let's examine the eigenmodes of the entire model. Select all the elements. The eigenmodes are displayed for the entire model. Change the number of columns for the image alignment, reduce the image size, in order to view more eigenmodes at once. More eigenmodes can be seen by scrolling the image. There are 3 rigid body modes also for the entire model, and they are equivalent to the rigid body modes in a single element. In fact, the 3 rigid body modes make essential contributions to displacement behavior of a plane strain model. However, zero-energy modes are not always rigid body modes. There may exist deformation modes with 0 eigenvalues, which are called spurious zero-energy modes. Existence of spurious modes depends on the numerical integration scheme applied to computation of stiffness matrix. Click Integration Option button to change the numerical integration scheme. Integration scheme dialog pops up. Choose the 4-node quadrangle from the drop-down list of element shape. Current setting is 2x2 integration. This can be changed to 3x3 or 1-point integration. Let's examine the case of 1-point integration, which may cause a rank deficiency of the stiffness matrix. Now, the display shows the eigenvalues of the entire model, applied with 1-point integration. There are 5 zero-energy modes. However, only the first 3 modes are identified as rigid body modes. 2 additional zero-energy modes are called spurious zero-energy mode. A spurious mode has a 0 eigenvalue, but the representation of its eigenvector looks abnormally deformed. This indicates that spurious modes may cause instability of the finite element solution. Let's examine the spurious modes at the level of a single element. Click an element. The eigenmodes are displayed in wireframe. The eigenmodes of an element also include 3 rigid body modes and 2 spurious modes. Let's change the display to contour image. The spurious modes have variation of strain energy density within the element, although corresponding eigenvalues are 0. Display the integration point. It should be noted that the strain energy density vanishes at the integration point. This explains why the eigenvalue, that is, the strain energy, is evaluated as 0 in spite of the deformation of the element. Let's examine the case of assembled configuration. Select two adjacent elements. There appear 3 rigid body modes and 3 spurious mode. The animation indicates the mechanism of spurious mode for the assembly of 2 elements. The spurious mode with such a mechanism is a so-called hourglass mode. Let's examine the case with assemblage of 4 elements. Three rigid body modes are preserved. But there still remain 3 spurious modes. This is a communicable mode, which cannot be controlled by assemblage of elements. In order to take an example of non-communicable spurious mode, let's examine the case of an 8-node quadrilateral element. The same model will be used with 8-node elements instead of 4-node elements. Close Eigenmodes window and choose Make Quadratic Item from Mesh Refinement submenu. A notice message appears. Click OK button. Then, all the elements are converted from 4-node to 8-node quadrilateral elements. Choose Eigenmodes item again, from FEM Simulation submenu. Eigenmodes window opens. Select an element. Then, the display shows 3 rigid body modes and 1 spurious mode. Change the display to contour image and mark the integration points. As in the previous case, the strain energy density vanishes at the integration points of the spurious mode. Let's examine the eigenmodes for assembled configuration. Select 2 adjacent elements. This time, there appear no zero energy modes. It is because both of the elements cannot display the same spurious mode while they are connected. This is an example of non-communicable mode. Let's examine the case of 4 elements. Assembly of 4 elements also shows the same aspects of rigid body modes without spurious modes. Lastly, the eigenmodes of the entire model is to be examined. Select all the elements. The eigenmodes are displayed. Change the number of columns. Adjust the size of the images and gaps between images. 3 rigid body modes are identified, and other modes show normal behavior. As mentioned earlier, the rigid body modes are essential components for proper displacement behavior. On the other hand, the rigid body modes correspond to linear dependency of finite element equations, and therefore, should be constrained for unique determination of the displacements by finite element analysis. The rigid body modes are constrained by assignment of boundary conditions. Close the Eigenmode window and choose Boundary Condition item from Assign menu. Assign the condition of horizontal roller to the bottom edge and vertical roller to the left edge of the model. Start Eigenmode function again. Select the entire model. No rigid body modes are shown. Instead, the displacements, represented by eigenmodes, are constrained by the boundary conditions. So far, external forces applied on the model have not been involved in the eigenmode analysis. In fact, eigenmodes are determined independently of the force application. However, the contribution of each eigenmode to the model behavior is determined by the external forces. Close the Eigenmode window and choose Load Condition item from Assign menu. Let's define a load set as a uniformly distributed force with magnitude of 5. Assign the load set to the right edge of the model. Solve the analysis model. The model data should be saved to a data file with designated name. Save the data. The solution process is completed. The analysis results are now available, and can be displayed using Post-Pro menu. Choose Display Item of Deformed Shape submenu. Set the options for deformed shape image. Adjust the distortion factor of the deformation scale and the scale of the image. The deformation of the model can be interpreted as a linear combination of eigenmodes. Start the eigenmode function again. Select the entire model. The eigenmodes are displayed. Change the number of columns for eigenmode images. Adjust the size of the images, so that more images are visible at once. Scroll up or scroll down the image to make the hidden images visible. This time, there are additional information about the eigenmodes. C is the modal combination coefficient. The deformation of the model can be regarded as a weighted sum of eigenmodes, each of which is applied with the corresponding modal combination coefficient. Display of C values can be turned on or off. F is the force contribution factor, which represent the contribution of each mode to the deformation in energy sense. Display of F values can also be turned on or off. This is the end of the demo. The concepts introduced in this demo will be extended to the next demo about dynamic vibration analysis based on mode superposition.